Good evening, everyone. Welcome to the 2017 Tuzo Wilson Public Lecture. My name is Qingya Liu. I'm a geophysics faculty at both Department of Physics and Department of Earth Sciences. Thanks for coming. I'm so glad to see such a great turnout. Now, this Tuzo Wilson Public Lecture Series is an annual event put on by the Department of Physics at U of T. Each year, we commemorate the life and work of John Tuzo Wilson, who was one of the key discoverers of plate tectonics. Now, as you know, plate tectonics is to geoscience as Darwinian evolution is to biology. It is the framework into which everything else fits. Tuzo Wilson made a series of famous contributions that established plate tectonics starting a bit more than 50 years ago, some of which you have been seeing on the screen behind me here. The answer to his famous question, did the Atlantic close and then reopen, is a resounding yes. This opening and closing is now called the Wilson cycle. Our speaker this evening, Peter Molnar from University of Colorado Boulder, follows very much in Tuzo's footsteps. He's a world leader in the modern understanding of plate tectonics. Among many other awards, he received the 2014 Crawford Prize for Geoscience from the Royal Swedish Academy of Science, which is sort of like the Nobel Prize for Geoscience, and considered by many to be even more difficult to get than Nobel Prize, because the awardee is picked from multiple fields such as astronomy, math, geosciences, and biosciences. He was honored for his groundbreaking contribution to the understanding of global tectonics, in particular the deformation of continental and the structure, the deformation of continents and the structure and evolution of mountain ranges, as well as the impact of tectonic processes on the ocean atmosphere, circulation, and climate. So please join me in welcoming Professor Peter Molnar.
Thank you, Qingya. I can't see you if you can see me here. Thank you, Qingya. This, when I was invited to give this lecture, this was a huge honor because, as you can appreciate, Tuzo was a giant in our field. But for me, it was special also because I met him when I was a graduate student, and I interacted with him for many years while I was still quite young. And he always treated me with respect as if I was just like him, one of the group. It was really quite an honor. This talk today is a little unusual in that it's more a collection of short stories than one story that starts at the beginning and then gets to the end. And it'll be clear, I think, when I change stories, at least I hope it is. Where I want to start is where Tuzo was back 50 years ago or so, and then move quickly through that up to other work that I was involved in with continents, and then move into climate. I contend that if he were alive today, he would probably be focusing on climate. This would be where he would be most excited. So let's move on. This is a map at the bottom, a topographic map, and at the top a map of plates as we know it, with lithospheric plates. The dark blue is the deeper part of the ocean. The lighter colors is shallower. This is the mid-Atlantic ridge going down between North America and Eurasia, separating the North American plate from the Eurasian plate, the North American plate from the African plate over here, down through between Africa and South America, again separating plates as we know it in plate tectonics. In the Pacific, the East Pacific rise heading down through the Pacific in here. Now, the basic idea of plate tectonics is that the Earth's surface can be divided into a number of plates that behave as rigid objects. The lithosphere is the plate. The lithosphere is roughly 100 kilometers thick, and these move apart at mid-ocean ridges. They slide past one another at what we call transform faults. This was Tuzo's term. And one plate plunges beneath another at subduction zones or island arcs, as we have here. And they can plunge beneath one another in opposite directions and be connected by another transform fault. This picture, this cartoon, was drawn with the South Pacific for a prototype for the South Pacific. The East Pacific Rise coming down the middle, a transform fault. The ridge comes down, steps across at a transform fault in here, as Tuzo had drawn it. The Nazca Plate, the plate on the east side, plunges beneath South America, beneath the Andes on this side, is drawn here. The Pacific Plate on this side plunges beneath the Tongan Arc over on this side, but the Australian Plate plunges northeastward under this region, and you have another transform fault connecting these up between them. Now, if we look at the whole globe, we have plates all over: North American Plate, African Plate, South American Plate, Nazca, Pacific. Some of these are very large, but there are some small plates, the Easter Plate and the Juan Fernandez Plate in here. There's no, we don't yet have a lower bound on how small plates can be, although they presumably can't be much smaller in horizontal dimensions than 100 kilometers or so. If we blow this area up and look at it, we're looking at this area where the southern of those is the Juan Fernandez Plate, the northern the Easter Plate. Looking over here, East Pacific Rise coming down past this, then heading in with big transform faults. And if we look down here, blowing this region up, we have these small plates, Easter and Juan Fernandez Plate. And if I just take these apart, you can see quite clearly the topography that surrounds these small plates. So just where are we with plate tectonics, or where were we 50 years ago? Plates are rigid. These thin plates. The word plate was first used by Tuzo in one of the papers that was shown earlier. There are three types of narrow boundaries. Where they separate, we have mid-ocean ridges. Where one slides past another, we have transform faults, there, or over here. And where they converge, subduction zones where one slides beneath the other. We have deep sea trenches there, island arcs, sometimes at least where there are islands out there. The Aleutians is a good example. And these rules apply even to small plates. Now, if we go to continents, that doesn't work. This is now a map. It's aligned in a strange way for a good reason, but here's India down here. This is the Tibetan Plateau up in here. The Himalaya are along the southern edge, and each of these blue arrows shows the velocity of a GPS point, a GPS benchmark that's been put in the ground and then measured several times. It's the velocity relative to Siberia, way up here off the map. You can see India is moving northeast towards Siberia, but when you look around the corner out in here, Tibet, it seems to flow around the edge. Flow is the operative word in here. You don't have rigid bodies moving past one another. It looks like continuous deformation in this region. Now, I want to show you this in a different way, where we hold India fixed. We have a lot more data since this time. India will be fixed, and we look at movement relative to India. So here's India down here. This is fixed. This is defining our reference frame. The green arrows are ones that we throw out because they're either large errors or they're aberrant in some way. But if you look along the Himalaya in here, what you can see is that out here in the western part, the movement is perpendicular to the edge, perpendicular to the Himalaya, and you can see that radially coming across. Over here it's southward, and it's even south-southeastward. So one has this divergence of the motion of the Himalaya in southern Tibet. And of course, as you know, if two of us are standing next to each other and one goes that way and the other goes that way, we'll diverge. This is what's happening here. These two are diverging from one another, so you have to be extending the crust between them across this region. And this isn't as clear, what I want to say, but what we think this is continuous deformation. The whole region is deforming as if it's a fluid. And in fact, the homely analogy we like to use is Tibet is just a humongous piece of ripe camembert cheese. It's out of the box. It's on the Indian plate here. It spreads apart, and it thins. It becomes thinner. This is a better image of how continents behave than plates, for sure. And I want to take this further now with an animation looking at a cross-section through here. India to the south, we're looking west. The rest of Asia to the south, we're looking 60 million years ago. Blue showing oceanic regions. The brown is crust. It's the outer light part of the Earth, thicker under India than under oceanic regions. This we've known for many decades. The red is the mantle. The dark red is the the lithospheric mantle, the strong part of the mantle. The brighter red is the asthenosphere. This deforms easily, this convex, and is not strong at all. So I'm going to run this animation. So just watch northern India. It slides underneath, a new fault breaks through, another new fault breaks through. Here we have the Himalaya. The Himalaya consists of stack of rock that's made from India. All of that rock lay back south on India. It was not part of the rest of Eurasia until the collision. Now let me run this again, but this time focus on the area that becomes Tibet. The crust over here thickens over a large area, becomes much thicker than the surrounding regions when we grow this high plateau in here with thick crust. So the difference between continents and oceans where we have plates that are like blocks that we play with as children. This is a little bit of a deception because really these should be plates. They should be much thinner than they are laterally in extent. And plates can be small as we have in the Pacific. Whereas when we're in continents, we have fluids or viscous fluids like cheese that deform. And why is this? Well, if we make a profile of strength through the lithosphere, through the upper mantle and the crust, in an oceanic region, the crust is thin, only about 7 kilometers. We have water above it. This is a plot of strength versus depth. And strength in the upper part increases with depth because the resistance to deformation is given by friction. And you all know when the winter comes and you want to be safe on the road, you put more sand in your trunk because you put more weight on your wheels. That increases the frictional resistance. It keeps the car more stable. Of course, pressure increases with depth, so the frictional resistance increases with depth. But eventually you get to a depth where rock can flow easily. It behaves plastically or viscously because of temperature. Hot rock will deform easily. It's like butter. You take the butter out of the refrigerator, it's hard. Let it sit out for a while and eventually it becomes much softer and it can flow. So the strength then decreases into the mantle. The depth scale here would be of order 100 kilometers or so, markedly with depth because of temperature, because of increasing temperature with depth. Now when we look at continents, it's different because the continental crust is made of different minerals, quartz and feldspar, and these flow viscously at lower temperatures than the mantle minerals like olivine. Quartz, for instance, can flow easily at as little as 350 degrees Celsius, where you have to get olivine up to 700 or 800 degrees Celsius. So where you have thick continental crust in here, you come down with brittle strength, but then you have this weak zone because the minerals can flow. It may increase in strength because of slightly different mineralogy at depth, but you take this big core of high-strength material that you have in oceanic regions, you take it out. Continents are just intrinsically much weaker than oceanic lithosphere. And except where continents are very cold, continental lithosphere is much weaker than oceanic lithosphere. This accounts for why we have plates in the oceans and why we don't have plates in the continents. So let me just summarize this before I move on in a different direction. Plate tectonics works because we have strong lithosphere, it makes plates. Plates behave as rigid bodies regardless of their lateral extent. We even have these small plates just a couple of 100 kilometers across, like the Easter plate or the Juan Fernandez plate. Continents, however, deform as continuous media, like honey, molasses, soft cheese, behave very differently. The rules of plate tectonics, relative motions of rigid plates, simply don't work where continents deform. This doesn't work. And continental crust can thicken to build high mountains and high plateaus. We have thick crust in here. I want to take this last bit a little bit further. Imagine a region, a high region, we'll consider this a fluid for the moment. This might be a water tower supported by walls with pressure, with forces on the margins that hold this up, keep it from falling apart. The pressure increases with depth. The same is true in a continental region. The high regions, of course, you go down to sea level, you've got a heavy weight of rock above you, so the pressure increases. Pressure increases with depth, and at the bottom, the pressure is proportional to the height. The height of here, the column of fluid, or in the case of Tibet, the height of the whole region. The height serves as a pressure gauge, and we look at Tibet as the pressure gauge of Asia. India moves towards the rest of Asia. It's built all this high terrain, but this is behaving like a pressure gradient. It is simply transmitting the force per unit length that's applied along the margins further north, causing deformation further north in the Tian Shan and up in Mongolia in this region, and presumably squeezing material out to the east. Okay, I want to change directions now. As I said, I think that if Tuzo were alive today, he'd be working on climatic questions. And so I want to talk about the monsoon. The reason I'm going to talk about the monsoon is I got interested in this because I was sure that somehow Tibet was key to understanding the monsoon. And I say I was sure because this is what I was told. Everybody else said this. I'll show you that that's probably not correct, or it's an exaggeration. But anyway, I want to move on and talk about the monsoon. So we all think of the monsoon as heavy rains over India, as is shown in this picture. But let's back up a little bit. What's the meaning of the word? The English word came through the Portuguese, actually. Monsoon has its origin in the Arabic word mosim, meaning season. And this goes back hundreds of years, because back many centuries ago, Arabs coming from Arabia, here's a map showing you Arabia, here's India over in here, coast of Africa. This is a plot of winds, colored over here in meters per second. This isn't at the surface quite, but the winds reach to the surface, of course. Strong winds blowing to the southwest in winter. So the Arab traders would come out of Arabia, pick up these winds and go down the coast of Africa, where they would trade for, well, let's not talk about what they traded for, but anyway. And then they would come back in the summer because the winds would blow the other way, and even stronger. These strong winds are, the seasonal cycle in these strong winds lie at the root of the word monsoon. If we look at rainfall, first let's look at topography. A map, Tibetan Plateau, India, Sri Lanka down here. The arrows are showing the winds during the summer, June, July, and August. And if one looks at where the rainfall is concentrated along the coast of India because the winds are blowing moist air in here and then up over a wall of mountains, the Western Ghats over here. So one gets orographic precipitation. The moist air rises, it cools, the moisture condenses, and it rains out. The same is true over in very small mountain ranges over in here. All this rain is, again, the orographic effect of winds blowing moist air in onto these mountains and up over these mountains. And then you can see the Himalaya provide a barrier where one gets rainfall in here. This little piece is associated with the Shillong Plateau. But over most of India, the rain isn't that much heavier. Over here's a scale, 600 millimeters per month. That's 20 millimeters a day. That's heavy. But you get into the dark blue areas and it's much lower. It's just a few millimeters a day. Now the conventional view here is that Tibet becomes hot. So this is a profile looking towards the east. Here's the equator, 35 north, profile of topography, of course exaggerated, with Tibet in here. The standard logic is that Tibet becomes hot because it's high. It's nicknamed an elevated heat source. The air here is hotter than it is over the same elevation over much lower terrain. So this hot air rises. As it rises, it has to be replaced. Moist air then blows in. The moist air rises. The moisture condenses. When the moisture condenses, the air heats further with latent heating, and one gets this cross-equatorial circulation. This is the standard view. The more contemporary view that's arisen just in the last 10 to 15 years says the key quantity is moist static energy. This is energy per unit mass over here. And it consists of three terms. One that depends on the temperature. Cp is the heat capacity at constant pressure. So this is how hot the air is. The second depends upon the vapor. Q is specific humidity, but more precisely, it's the concentration of water vapor in the atmosphere. LV is the latent heat. You all know that if you evaporate water, you have to put heat into that water to convert the liquid to a vapor. So the vapor contains energy, the latent heat that's gone into it. If you condense that vapor into liquid water and it rains out, you gain that heat, the latent heat. Gz is gravity times the height. This is potential energy. Remember, we're talking energy per unit mass. So this is This quantity, the moist static energy, is the mass in a parcel of air of a cubic meter if you like, or maybe even a cubic kilometer. It doesn't really matter. This is thought to be the key quantity. Now, an important part of this is that the really important part is the latent heat, not the temperature. The view with Tibet being important, and what drew me into studying the monsoon 25 years ago, and I could say that I wasted my time, but I've had a lot of fun, so it really doesn't matter. I focused here. This is really the more important quantity, the latent heat of vaporization that one gets from the moisture. So there are two simple elements to elementary monsoon theory. One, of course, has to do with moist static energy. The rate of ascent in the atmosphere maximizes, not over Tibet where it's hot compared to air at the same elevation, but slightly equatorward of the maximum in the moist static energy. So where you have high moist static energy, the air rises. This is due because hot air, of course, is more buoyant or it's less dense than cold air, but also water vapor is less dense than dry air. So both the water vapor that's in the Q and the temperature in the T, both of those make the air buoyant, and so it will rise. If you look at a map now, this is summer subcloud moist static energy, the moist static energy. This is just above the surface. The maximum is not over Tibet. So here's India, down here, Sri Lanka, Arabia, the coast of Africa. This black line here is meant to be the outline of the Tibetan Plateau. That's not an area of high moist static energy. In fact, let me point out that Arabia, which is sizzling hot, is not a particularly exciting place if your criterion is moist static energy, because it's dry. It's the moisture that really makes this. The maximum in the moist static energy lies over northern India. The second element of this elementary theory, you need a region of high moist static energy, that's for sure, but it has to be high enough to exceed a threshold, and that threshold increases with latitude. So, in more words, the farther from the equator, the greater the threshold. The threshold is set by the Coriolis effect, I might say. But also, if the moist static energy exceeds the threshold, the monsoon turns out to be stronger. And a simple analogy is water going over a dam. If you have a low dam, it doesn't take much water to get over the top of the dam, but you don't get much power. If you raise your dam and you bring in water, well, that water might all evaporate before it has a chance to go over the dam. You've got to get enough water to get over the threshold, but when you do get over the threshold, you get a lot more power than with a low dam. So this latitudinal dependence of this threshold in moist static energy is what makes India the strongest monsoon that we have in the world. So I'm going to move on with that. This is probably the hardest of all the slides I'm going to show you to explain the busiest one, work of Boos and Kwong several years ago. This shows, as you can see, 9 maps. Let's just locate ourselves first. Here's India. Here's Arabia over here. Coast of Africa, Madagascar, China over in here. These are calculations made with the general circulation model of the atmosphere for 3 cases, present-day topography. This black shows the Tibetan Plateau. This other black line is showing the Iranian Plateau and other high terrain in Asia, high terrain in Africa. One with no topography at all, and then one with no Tibet, but with a Himalaya. So Africa's still got high terrain, so does Iran. But now we don't have a Tibetan Plateau, we just have a Himalaya. We have just the southern edge of the Tibetan Plateau. The Himalaya make the southern edge of the Tibetan Plateau. Over here, in this column, are shown temperatures in the top of the troposphere. This is between roughly 6 and 12 or 13 kilometers. If you look in the top, where present-day topography, the maximum is over northern India, leaks into Tibet, but it's over northern India. This is where this maximum moist static energy lies. That's shown in this plot. This is where this hot, dry air rises, goes to the top of the troposphere, makes it hot. When you have no topography, you again have a hot area, not as hot, but the more important fact here is not the difference in temperature, it's the locus of hot air. It's way south. It's over the northern part of the Bay of Bengal. The center of this warm area is way down here, not as far north as India. If you have no Tibet, but you do have a Himalaya, again, the maximum of this hot air in the upper troposphere is way up in northern India. Essentially the same as what one has over here for contemporary topography. The middle is subcloud moist static energy, maximizing over northern India when in the present-day topography, maximizing over central India in the Bay of Bengal, much farther south. Note where that is. That's way down here on this plot, much farther south than this one. But when you have no Tibet, but you do have a Himalaya, again, you're back up with a maximum of moist static energy over northern India. Again, far from the equator, but enough to exceed the threshold in order to give a strong monsoon. And then rainfall, these models don't do a very good job with rainfall, famously poor job. But you get rainfall along the Western Ghats in India in both present-day topography and with no Tibet, but a Himalaya, you have it here. And you get rainfall along the Himalaya in both cases. But of course, when you don't have that topography, your rainfall is smaller, and again, it's farther south. Well, the important part is this part right here. So let's just look at that a bit more. What's happening? In this case, Tibet blocks cold, dry air. Cold, dry air is low moist static energy, right? Cold, small t, dry, small q. Tibet blocks the cold, dry air from the north with low moist static energy, and so the maximum moist static energy is over northern India, far from the equator. When you have no topography, you can see this cold, dry air, up here the blue, is leaking south, and it's just penetrating south, and it's mixing with the hot, moist air that one gets over India and over the Bay of Bengal. Tibet does not block the cold, dry air with the low moist static energy. Instead, the maximum is over central India, farther south. Again, without Tibet, but with the Himalaya, you still have the barrier. You still block this cold, dry air. Clearly, it reaches much farther south in this case than it does in that case. But it's blocked and it can't mix. The Himalaya, not Tibet, blocks the cold, dry air. And so the maximum, again, is over northern India. That barrier is the key to India having a strong monsoon. That plus being able to have enough hot, moist air over India to have a high moist static energy and overcome the threshold that's there. So how does Tibet affect the South Asian monsoon? It blocks the flow of cold, dry air with low moist static energy, again, and it prevents that cold, dry air from mixing with the hot, moist air over India. But this then leads to the question, well, Tibet isn't important, the Himalaya does the whole job. And this is, I think, where this field is right now. The Himalaya is important, but you don't need Tibet. Tibet helps a little bit, but it's not the key to having a strong Indian monsoon. The key is having a barrier of mountains that reaches all the way into Afghanistan over here that prevents this cold, dry air from coming in. Okay, I'm going to change again. I told you this is a series of short stories. This, I don't think this is a subject that people argue about, but I'm going to end by going a little further, much more speculative, and I'm going to tell you a story that is the sort of story that if Tuzo Wilson told it, it would turn out to be right. And so I'm giving it here at this audience, I want it to be right, but you'll see that it's a very speculative story. So we go back to small plates. We're going to go back to Indonesia. This is a kind of an erratic story because where we're going to wind up is over here in Canada. But we're going to go back to Indonesia where we have lots of small plates. Just to orient you, this is the Malay Peninsula, Indochina, the border of China in here, Taiwan, Philippines. This is Borneo, Sumatra, Java, New Guinea, the northern edge of Australia. And clear maybe is with GPS again. These are velocities. Each of these red arrows is a GPS point. There's a little island out here where there's a GPS point. Measured, in this case, relative to what we call Sundaland. This region in the middle includes Borneo, the Malay Peninsula, most of Sumatra over here. So India is moving north-northeast, sorry, not India, Australia, the Australian plate, here's Australia, moving north-northeast relative to Sundaland. But when you get into these smaller blocks in here, or smaller plates, very fast motion in very different directions. Some of these islands are moving as much as 100 millimeters a year west, not parallel to Australia's motion. So lots of relative motion of small plates in here, small plates of the same dimensions as the Easter plate that I showed you earlier. But there is an important difference. And that difference is there's a lot of relief on these. These have crust that can thicken. You can thicken crust, you can make mountains, and you make islands. Islands are going to be crucial. So The light colors in here are showing high terrain in Borneo, Sulawesi, high terrain. New Guinea has a belt of high mountains going through the middle of it. Mountains, mostly volcanoes along in Sumatra over here. Now, as I said, this is speculative. Where we're going is ice ages. So we're going to go to Canada, and I'm going to argue that it's the islands of Indonesia, or what we call the Maritime Continent. It's those islands that, the growth of those islands that have given us ice ages. So just to remind you of what an ice age is, this is an animation, another animation that Tanya has made. And at some point, ice builds up over around the Hudson's Bay, moves south, we lie way down. Right now, we're down in here, comes into the United States, it wiggles around, and it retreats. This has happened 50 times in the last 2.5 million years. 50 times, roughly 50 times. In the 250 million years before, 2.5 million years ago, this didn't happen at all. So something happened in the past few million years that made it possible to have ice ages. Well, what's the key to making an ice age? In very simple terms, you want to prevent summer warmth from melting last winter's snow. If every summer you melt the snow from the previous year, you'll never build up ice. If you can stop this so that next winter's ice can accumulate on, next winter's snow can accumulate on last winter's snow, you can start to build an ice sheet, and if you build an ice sheet, then you can make an ice age. And how do you do that? Well, you either cool or you shorten the summer. You want to make the summer less effective as a melting device for getting rid of last winter's snow. Well, the common strategy with this in modern earth science is to look at modern day examples and see if we can understand modern day examples. And the example that we rely on heavily is El Nino. You probably all hear of El Nino, at least starting 25 or 30 years ago when it became popular. When an El Nino occurs, and I'll talk about this more in a second, the whole world responds. In particular, Canada is much warmer. The ice on the Great Lakes is thinner, and Canada is a warmer place. Southeastern United States turn out to be wet and cool. The Amazon becomes dry. There's this global response to El Nino, but for the purposes of what I'm talking about, Canada becomes warmer. We can look at this a bit more quantitatively in another way, with what's called positive degree days. The logic here is you take this symbol, the sigma shows a summation, and we're going to have I vary from 1 to 365. I equals 1 is January 1st. I equals 365 is December 31st. And we take every day, and we look at that day, and if the temperature is positive, greater than 0 degrees C, we keep it. So suppose on January 1st, the temperature were 5 degrees Celsius. We would have that day we would have 5 degree days. Suppose the next day it were 10 degrees Celsius. Well, we add that and we're up to 15 positive degree days. January 3rd, the temperature is minus 5 degrees C. Well, if the temperature is negative, we don't keep it, multiplied by 0. So we still have 15 positive degree days. And we add this up for the whole year. Imagine if you had every day the temperature were 10 degrees Celsius. At the end of the year, you would have 3,650 positive degree days, 365 times 10. Here's a map showing where there are stations, and you won't be surprised. Here is the pole in the middle, Greenland. You have more positive degree days at low latitudes than you do at high latitudes. Well, of course, it's warmer at lower latitudes. What happens during El Nino? If one looks at El Nino events, we're now looking at this plot. We're not looking at a scale of thousands, we're looking at a scale of hundreds over here. But during El Nino events, Canada has more positive degree days, has more by order 200. You might think, well, 200 is a small value compared to thousands, but in fact, it's quite a big number. 200 positive degree days can melt 1/2 to 1 meter of water equivalent ice. That's ice of density virtually the same as water, or equivalently 5 to 10 meters of light snow, dry snow that's fallen. That's a lot of snow. Most of Canada doesn't get that much snow in a year. So 200 positive degree days is enough to throw you over and prevent you from, how do I say this? If you have El Nino, 200 positive degree days will melt last winter's snow without too much difficulty. What happens during an El Nino? These are two maps. You'll notice New Guinea, Australia on this side, Mexico, South America. These are maps of sea surface temperature. Sea surface temperature plotted here, getting up to 30 degrees Celsius. Western Pacific is warm. This is called the warm pool. The Eastern Pacific is cool along the equator. This is called the cold tongue. This is the average standard conditions. We sometimes call this La Nina. I'll say more about that in a second. During a big El Nino, the whole Pacific becomes warm all the way across. It becomes much warmer by several degrees C in the Eastern Pacific. And it's this warm Eastern Pacific that then connects to Canada and to other parts of the world through teleconnections that make Canada warmer. Well, what do we see for a history? I'm going to show you a plot here, a temperature history, taken, measured with paleoceanography from a site over here. All these are oceanographic places where deep sea drilling ships have bored into the sediment and made measurements. And this one is from over here. The red line, don't worry about the blue line. The red line is showing inferred temperature on this axis in Celsius, degrees Celsius, getting up 26 degrees, going back in time, 1, 2, 3, 4, 5 million years ago, and you see a steady decline, going from roughly 4 degrees Celsius warmer back 4 million years ago than today. So what we've done is we've gone from an El Nino-like state where it was warm in the Eastern Pacific, like this, to the present day La Nina-like state here. And by going from El Nino, where we could melt last winter's snow, we could prevent an ice age from beginning. Now, when we're more commonly in this state, we have the potential for building ice there. So let me give you a summary where we are. I'll pick up on this in a second. So imagine a world with a permanent, average, El Nino-like eastern equatorial Pacific sea surface temperature, this configuration. Then by analogy with that, with modern El Nino teleconnections, atmospheric heat transport from the tropics to high latitude North America before, roughly 3 million years ago, sufficed to melt the winter snow and prevent ice sheets from growing in Canada. This warm area in here prevented this because we had an El Nino-like state. This leads to the question, okay, what geologic process transformed the eastern tropical Pacific from El Nino-like, this, to La Nina-like, this? And now I go back to Indonesia. I'm going to go back to Indonesia with rainfall, but more importantly, with convective rainfall. So just to warm you up, this is a photo one of the great physical oceanographers, Arnold Gordon, took. This is a convective storm. Here's the sea surface, obviously. Very rapid ascent of moist air. It's raining in all of this. It hits the top. This is the top of the troposphere. This spreads out, makes this anvil up in here. Big, big thunderstorm, big cumulus convection. If we look at Indonesia in terms of daily rainfall, or the Maritime Continent, let me just read you this quote from a paper long ago. "The afternoon convection provides a near-perfect map of the region. Every island and mountain range is delineated by one or more cumulonimbi." And if you look at this, all these islands have lots of rain on them. Borneo is a little less spectacular. If we take Sulawesi and blow it up, the arms of Sulawesi are outlined by rain. Even little islands have rain. Halmahera has loads of rain up in here getting into New Guinea. Rain over Flores in this area. The islands are attractors for rain, and I'll say more about that in a second. But if we go back in geologic time, here's the present, the black showing where we have islands, Borneo, Sulawesi, New Guinea, northern edge of Australia. If we go back 5 million years ago, much of this was submerged. Much of New Guinea was underwater. Halmahera was mostly underwater. Ceram was underwater. Timor was underwater. A lot of Sulawesi was underwater. Not much of Borneo was underwater. A good bit of the Philippines were underwater. Today, it's approximately 18% island in the Maritime Continent. Maritime Continent because it's continent, but it's mostly water. At this time, there was only 11%. So we've had an increase in the islands, and you've seen that the islands are attractors for rainfall. Okay, let me take this further. I'm going to show you now an animation made by Tim Cronin. This is, again, results from a cloud resolving model. This is a very high density model. There's a map in here, 370 kilometers on each side. We're looking 15 kilometers up into the atmosphere. These white areas are showing clouds where it's raining. Blue is where there are downdrafts. This region in the middle is an island. And now I have to start this. It starts at midnight local time. The island is cold and it's going to cool because it's going to radiate heat up into the sky. There's nothing blocking this heat. It's going to radiate, and then a little bit later in the morning it's going to turn and get hot because the sun is going to shine down on top of it. There it goes. It starts to get hot, heats up a lot. You can see it gets much hotter than everything else. Then the hot air rises, it draws moisture in, you get big rainstorms, convection all over here, downdrafts, bringing cold air down, spreading out over the whole area, and we're back at midnight. I'm going to go through another 24 hours here, or the better part of 24 hours. At night, you have rain all around. That's happening. Again, the island is cooling. It's cooling because it's got clear sky above, radiates heat up into the sky, cools down until late in the morning, and then it heats up very quickly again. Hot air rises, the air is rising, induces convection again, heavy rains over the island, and then the downdrafts spread out over the whole region. It turns out, this was quite a surprise, if you compare a case, the difference in air temperature between runs, calculations with this model, with and without an island, the air is much warmer when you have an island than when you don't have an island. This has no dimensions to it. This is just the shape of the function. It's much warmer at the top than the bottom. This blue is showing you that the surface is a little bit cooler. This is pressure rather than kilometers in height, but we're going up to 15 kilometers up in here. So the air is heating over this region. Now Tim ran another simple model. This is now a 2D model to try to understand this or to illustrate what's going on. What happens is he puts in heat at the bottom, down here, same amount of heat everywhere, puts heat in at the bottom, takes heat out at the top. But in the middle, between these bars in here, he varies the heating with a diurnal cycle, heating in the daytime, cooling at night. And when he does that, even though the same heat comes in here as out in there, with this diurnal cycle, it sets up a circulation where you have ascent over this area. The red is rightward flow. Blue is negative, it's leftward flow. So you have divergence aloft, convergence down here, and this mean wind pattern of ascent over this place where you're heating diurnally and then spreading out. Over here is a plot then of the vertical component of velocity in this area over the place of diurnal heating, and of course the maximum is in the middle in here. What's going on is when you heat the surface down here more than normal, as you would in the daytime, the hot air rises, goes all the way up. When you cool at night, this cold air merely spreads out on the bottom. So this rightward flow in here and leftward flow on this side is just cold air near the bottom flowing out. In the language of electrical engineering, this is rectifying the diurnal cycle, half-wave rectifier, giving you this net ascent and net ascent of hot air. So you're heating the troposphere above. So we go back to this plot of how the temperature varies with height, and now plot the dependence of the difference in temperature between with an island and without an island as a function of the fraction of island area. So 0 means there's no island. Getting up to more than 20% island, you see this increase. In fact, today at 18% island over Indonesia, this would suggest the temperature over this region in the upper troposphere should be 1.5 degrees C warmer than it would be if you had no islands. 1.5 degrees C might not seem like very much, but if one looks today across the whole Pacific, so here's the Maritime Continent, Borneo, New Guinea, Australia, here's South America. This is the temperature in the upper troposphere, around 12 kilometers. Temperature here is, you wouldn't call it hot, minus 40 degrees Celsius, but it's only 1.5 degrees C warmer than the temperature off in the east. It's a small difference. The atmosphere can't support a large difference in here. But the point is that this diurnal cycle is making the upper troposphere warm. So give you a quick interim summary again. The islands attract rainfall because of the diurnal cycle, the daytime heating, the heating where then the hot air and moist air rises. Heating over the island causes warm, moist air to rise. Cool air merely spreads out over the surface. So the cool air doesn't have the opposite effect. The rising warm air then maintains a hot troposphere, not only just over the island, but over all the surroundings. In this case, in that whole box, 370 by 370 kilometers. Well, how does this fit into El Nino? Today, we have this warm pool in the west, the cold ton in the east. Hot air rises over the west, goes aloft, moves to the east when it's high in the atmosphere, subsides over the east, and then strong winds blowing from east to west pile up this water to make the warm pool. This circulation is a near steady state circulation. It breaks down during El Nino. During El Nino, when the whole Pacific becomes warm and these strong westerly winds become weakened or disappear completely. So we have this different circulation. It's dependent on the ascent over the Maritime Continent and the Western Pacific. And we can quantify this as well. If we look at the simple cross-section of this Walker circulation, the Maritime Continent here, ascent over here, islands, air is rising, eastward flow aloft, subsidence in the Central Pacific or farther east, and then this westward flow along. This is called the Walker circulation. As I said, this is a near steady state, broken down only during El Nino events. If we correlate rainfall over the islands in Indonesia with the strength of this circulation, what we find is 1 millimeter per day more rain over here will give you 3 meters per second stronger Walker circulation, stronger winds because of more rain. So I think you can see where I'm going. More rain falls near the islands. Islands are really important. More rain over the islands means a stronger Walker circulation, stronger easterly winds blowing across the Pacific. A stronger Walker circulation means a cooler eastern tropical Pacific, cooler as we have most of the time during a La Nina-like or background state, cooler than, of course, what I'm going to argue is we had before, cooler certainly than during El Nino. So more islands should mean more rain and a cooler eastern tropical Pacific. Add islands to this area and you get a stronger Walker circulation. A cooler eastern tropical Pacific means fewer positive degree days, therefore a shorter summer over Canada. And fewer positive degree days then allow winter snow to survive the summer and build up and make an ice sheet. So you add islands. The red is showing you land the red is showing you land today, but 5 million years ago the red was submerged. The black is showing you land both today and 5 million years ago. So add islands to the Maritime Continent, increase rainfall, strengthen the Walker circulation, cool the eastern Pacific, shorten summers in Canada, and let ice ages begin. As I said, this is if Tuzo said this, it would be right, I'm sure. And I get to say it here and pretend I'm Tuzo. This is quite an opportunity. So just to tell you where I've been, first we started with small plates. Plate tectonics, small plates. We have these small plates in the Pacific. Then we went to Asia, where we have continental deformation. We make high mountains indeed, but our Tibetan Plateau is really just a big piece of camembert cheese. From there, we came across to the monsoon, and unfortunately Tibet didn't play a very important role in that. Disappointment to me, but I can live with this. The Himalaya is all it takes to have a strong monsoon. Then we go over to Indonesia or the Maritime Continent, where we have more small plates, but we have growing islands, and we have heavy rainfall, and that's crucial. That allows us to shift from an El Nino-like condition, where the Pacific would have been warm all the way across, or certainly warmer in the east than it is today, switch to the present-day La Nina-like conditions, where it's warm in the west, cool in the east, and then that allows us to have ice sheets on Canada. Thank you.
Thanks for this very interesting talk and the world tour you're taking us. So we're going to open up, the floor for questions.
Do the ice ages, or did the ice ages in Europe have a connection with the ones in North America, or do you see a different motivator there?
I guess the first thing I should say is I'm not an expert on that. I think there's little doubt that they're concurrent. So when you had ice in Canada, you had ice over Scandinavia and Finland, Finno-Scandia. Those, at least recently, they're contemporaneous as far as we can tell. How they're related to one another is another question. My own belief, which I can say here and pretend to be Tuzo with, but maybe isn't all that strong an argument, is that they're really slave to Canada. If you put an ice on Canada, you can make an ice age in Northern Europe much more easily because they're much smaller ice sheets than those over Canada. But I don't know that's really so. And we don't have the record. When I say there have been 50 of these, that doesn't come from data in Canada. That comes from marine records of other data. We presume they happen simultaneously in those two places, but we don't know that.
I'm going to ask a question. What about the Milankovitch cycle and the orbital parameters and blah, blah, blah?
Well, they're fundamental. So I skipped that. You might be saying to yourself, well, we don't have ice today. Why do we have to make it warmer? We've had ice ages when the Earth's orbit, the parameters describing the Earth's orbit were different. Of course, you know this. One of them is the obliquity of the Earth's axis. So if you tilt the axis down, obviously you put more heat into the poles. So when the Earth's axis tilted down, those were interglacial periods. When it tilted back up, we had glacial periods. The Earth's orbit also isn't a perfect circle. It's an elliptical orbit that goes around. And today, when we're closest to the sun, actually we're pointed this way, the southern hemisphere is close to the sun in its summer, and we're far. We get way out here. When we have summer, we're far from the sun, so we have less radiation on our northern hemisphere. That's precession. That's got a period of roughly 20,000 years. We get ice ages that are set by the tilting of the Earth's axis and by the precession. And we're in a funny time right now. We almost should be going into an ice age right now, but we're not.
I think we've stopped the ice ages now.
I'm not going to go there.
Other question?
Hello. You emphasize the size of these islands. No, the size of these islands in some ways is related to the ice age because of the oceanic level. So when there's an ice age here, so is there not a circularity or a feedback in this system?
That's a good question. And I guess the answer that I have to give is I don't know. But I think what you're saying, and others may not understand this, is when you have an ice age, you lower sea level, so you'd have a vast area that would have been exposed. So you'd have more island during an ice age. It would be exactly the opposite of what I'm saying. But the answer that we don't know, but the answer I would hope, in putting Tuzo's tie on to say this, is that you'd have such a huge area that they wouldn't be islands. You'd flood an enormous area, the whole from New Guinea all the way to Australia, from Borneo all the way to the Malaya Peninsula, that you wouldn't have islands at all. You'd have just a vast continent. And then you don't get the effect that you have with islands because it's too big. That make sense?
Yeah, but wouldn't you need an explanation for these 50 advances and retreat that you described in the last?
The 50 advances and retreats is Milankovitch. That's the orbit. The question I'm asking isn't how do we make ice ages 50 times. It's how do we get to a state with our climate that we can make ice ages with orbital variations. Sorry, I didn't make that clear. But why did we go from no ice ages for 250 million years or 300 million years to recurring frequent ice ages? We had to change something in the state that would allow us to have frequent ice ages, and that's what I'm trying to do with the islands here. Once we get to that state, then Milankovitch becomes the key to understanding that. Sorry, I should have made that clear.
Is there any reason to think that we might be shifting back to El Nino-like situation, or are we heading more in the La Nina type of direction?
That's a really good question, and it's very disputed. I don't think we know. There are two camps, right? One says yes, the other says no. The evidence does not suggest that we're going in that direction, but and I would contend that the models aren't good enough to be used to test this. That's another story. So I don't think we know. The people I trust most say, no, we're not going in that direction, at least not yet.
When you say that direction, you mean...
Sorry, are we going to go more towards El Nino as we heat the Earth? No. What my impression is we won't. You can imagine you make the whole Earth warmer, but for El Nino you need to destroy this gradient across the Pacific. And that gradient, there's feedbacks in that gradient that can sustain themselves regardless of what the mean temperature is.
So just a supplemental question. So even if the Earth is warming, are you saying that if we have more of this La Nina-like situation, then we actually can get ice ages with the increase in the temperature?
No, I certainly wouldn't go that far. With warming, we're not going to get ice ages, I don't think, for a long time if we keep warming at the rate we're going. What I would say is that the effect of warming doesn't affect El Nino very much, and if it does, it actually makes El Nino less of a part of our climate than it has been, though I don't have a lot of confidence in that statement. But as far as ice ages on another longer time scale, no, I don't think we're going to go. I don't think we're going to go back to where we were 3.5 million years ago, unless we keep warming the Earth and making it still hotter. I'm not sure I'm answering your question very well. I'm sorry.
Hi, thanks very much for your talk. That was really interesting. My question is, right off the top, you said that the theory that you've posited today is somewhat disputed. And so I'm curious to know what is an alternative theory that's been posited.
For the Ice Age question?
Yes.
Yeah, okay, there are, that's a good question. Remember, there are two parts to this. There's transforming a world where you had no ice for a long time to one with recurring ice ages, and then there's why we get the recurring ice ages, which Stephen asked me about. I skipped the second. What enabled us to go from a different situation? There are three, I'm aware of four possible explanations. One is that CO2 was higher a few million years ago, and it just was a warmer world. This is easy. People put these in their model calculations. They get it out. I don't find this particularly convincing. The evidence, the geologic evidence for past CO2 isn't very good. So let's ignore that one. The people I know who think about this hard are convinced that we have gone from an El Nino-like to a La Nina-like state. The question that we argue about is what geologic process did that? Let me say that a little differently. The geologic evidence from paleoceanography, looking at past oceans from the Pacific, is pretty good. That really does show us that the Eastern Pacific was warmer back a few million years ago than it is today. So that's good. How did we get there? The three ideas, I gave you one with islands. There's another one where, in fact, you change the ocean circulation. Indonesia moves north and blocks water. It's a complicated explanation. It's one that I like because a colleague and I actually proposed this too. And that moved New Guinea north. It blocked Pacific water, prevented it from going into the Indian Ocean, and made Western Pacific warm. There's no good evidence for it. It's a nice idea. The best idea may be that it's simply a cooling of the ocean. You can imagine if you have a warm ocean over a colder ocean, as we have, the cold ocean is protected from the sun by that warm cap on top. But if you can make that warm ocean thinner and thinner, the layer, the thermocline, make it thinner and thinner, winds can come and then blow it off. Blow off that warm water. you bring cold water up, and then you go from a state that was El Nino-like to La Nina-like. This is what George Philander at Princeton and Alexei Fyodorov at Yale argue. And it's a pretty good idea. It requires that the deep ocean be cooling steadily, that the thermocline be shoaling, the cold water is moving closer and closer to the surface, so that that warm top layer gets thin enough that then an instability can take it off. My ego is tied up with what I told you, and I like it, and I want it to be right, but what they propose is a really good idea.
Thank you.
Thank you. You've created a headache for me, so that means you did a good job.
You're the
I
first
don't
person
have-
who's ever told me that.
I don't have the technical language to ask this question. So you didn't mention the closing of the gap between North and South America. Can you talk a little bit about that factor and the ocean currents?
Yeah, I thought a lot about that. And so for the rest of you, there is a pervasive idea. Used to be you'd find it on Wikipedia. I give talks and show what Wikipedia said, that the Isthmus of Panama emerged 2.5 million years ago, and it blocked circulation between the Pacific and the Atlantic, and that this led to ice ages. I think this is just a beautiful example of nonsense. The logic of it makes a wonderful story. The logic is that animals passed from one hemisphere to the other, north to south, south to north. Lots of animals. Mammoths, mastodons went to South America. Cats. I can't think of all the animals. Of course, the camelids, the llamas, they're all North American derived. Going north were anteaters and possums and a whole bunch of others. And they all passed through around 2.5 million years ago. So everybody said, wow, that's when ice ages began. You must have brought Panama up so they could pass through. I think this is backwards. Panama has been there for 15 million years. What happened was you had ice ages. Those animals wouldn't go through now. The cats would go through, but the llamas wouldn't go through. Certainly the mastodons and mammoths wouldn't go through. What happened was we had ice ages, you dried out Panama, you made it a savanna. These are mostly savanna-dwelling animals, and they shot through. Oh, wow, we have a new place. We can go visit another hemisphere. So they all crossed because of ice ages. The ice ages have nothing to do with Panama. They are the cause of the ability of mammals to pass through that area. It's beautifully inverted logic. It's wonderful when you find in the 21st century scientists making such big mistakes and not thinking about these things.
In the context of past glacial cycles of supercontinents, to what extent does it matter at what latitude these mountains are being formed?
There are a lot of mountains. I don't, for glacial cycles, I don't think the Himalaya or Tibet or any of that matters. If you buy what I'm arguing, I'm not sure who asked the question, so I don't know if I'm looking at the right person. Oh, way up there. One of the things that we want to do and we haven't been able to do is look at what's the effect of topography on the islands. These calculations that I showed you that Tim Cronin made, it's a flat island. There's no relief. Orography will surely help. So if we can build islands in Indonesia, but also make them mountainous, I anticipate we'll get an even stronger effect. That's my hope. But do I know that? No, I don't know that yet. And it turns out this isn't easy. Well, it's not easy for us. There are probably people in the room who could do this, but it's not an easy thing to do.
And just to follow on that, in the context of the Coriolis effect and the energy intensity of the equator versus northern latitudes, does it matter for your hypothesis here that these mountain building events that are potentially influencing glaciers are being built at the equator?
No, in fact, in a sense, the zero Coriolis effect at the equator is really important for the Walker circulation. That's why you can have a small temperature difference across the equator and have strong winds, because the only friction is the only thing that's resisting the flow of the air. So it actually helps having a weak Coriolis effect there. The monsoon, the Coriolis effect, is in fact the threshold. If you don't get the pressure gradient strong enough, all you do is create easterly winds. You don't get a cross equatorial circulation. You've got to exceed a big Coriolis effect, and that's why the threshold increases with latitude. The Coriolis effect increases with latitude.
Yeah, this is about plate tectonics, specifically Pacific Ocean plate and Indian subcontinent. Pacific plate used to be moving more or less northward until 45 million years ago. It changed the direction to northwest to Japan at the Midway Island. Now that 45 million years ago was, as you show, Indian subcontinent hit the Eurasian continent. I wonder it's just coincident, or is there any underlying effect of mantle or something? I wonder.
Yes. So you're asking, you're pointing out, of course, that if you go out the Hawaiian Islands, Tuzo was really into this, out to the Hawaiian Islands, you hit the Emperor Chain, you have a big change in direction. So it's thought that that means the Pacific Plate used to be moving north, and now it's moving more easterly, westerly, where you have that bend in there. Actually, I think that's not very well established. If you do plate reconstructions, you don't see that. So I'm not convinced that that change in the orientation of the islands has anything to do with plate motion. Your second question is, India seems to collide with Eurasia around 45 million years ago. This is a big controversial topic right now, with people arguing about whether it's 40, maybe younger than 40, or even before 50 million years ago. And it's more complicated than what that animation showed. So the 45 million year collision here and the roughly 45 million year elbow in the bend is complete coincidence because of a bunch of conspiracy of a bunch of effects. Could they be related? I don't think so, but that's where I don't want to go there. So I think not.
Now you emphasize the ice ages over the last 3.5 million years, but other people define ice ages as something much bigger, the last 30 to 35 million years, prior to which there were no ice caps in Greenland or in Antarctica. Is there a similar explanation to that big ice age, or is that unrelated phenomenon?
Again, I'm not the expert, but indeed Antarctica, ice on Antarctica built up 32 million years ago. Suddenly on East Antarctica, you've got ice there. So before 32 million years ago, ice was a rare phenomenon on the surface of the Earth. And then you got a lot in Antarctica. And then it's thought that 15 million years ago, you got a lot more ice on West Antarctica, the part that's closer to South America. My, hesitate to say belief, but my understanding is that this has to do with the circulation around Antarctica, that the currents, that right now you can go all the way around in the water. So the currents are strong. The circumpolar current, circumantarctic current around Antarctica is strong. That, by being strong, it prevents actually warm water from getting closer to Antarctica, prevents warmth from being brought in because it can't get there. You can bring warm water quite far north in the Atlantic, up to Europe for one thing, but you can't get it very close to Antarctica because it gets stuck with the force balance of what maintains that current. So that is thought. So if you go back before roughly 32 million years ago, South America and Antarctica seemed to be connected. So you couldn't pass water through there, and it's possible that Tasmania lay up against East Antarctica down near McMurdo in that area. So again, you had a barrier, and you couldn't have this circumantarctic current. So that's the conventional view, that somehow opening those gateways so you could just go round, round, round Antarctica. That enabled ice, cooled Antarctica and enabled ice to grow there. Has nothing to do with anything I'm talking about.
Thank you.
Yeah.
Well, you discussed the west coast of North America. How frequent are the major earthquakes?
Whoa, sorry. First, what was the question again?
The west coast of North America, and how frequent are the major earthquakes?
Well, there's different settings. If you're talking about big earthquakes from Northern California north to Vancouver, they're about every 350 years, but sometimes you get 500 years between them and sometimes shorter periods. If you're talking about California along the San Andreas Fault, the recurrence interval, I don't think it's known that well, but it's in the order of 100 or a bit more than 100 years for the big earthquakes at any point. So doesn't mean you can't have, you could have two in 1 year, but they'd be different parts of the fault. Am I answering the question? This is something I think about, but it's not what I talked about.
I think we should consider this question over cheese and crackers at the reception. Let's thank the speaker again.
Thank you.